Hello everyone, this will be the third and final video on fluids, and this time we'll do fluid dynamics. So fluids, when they flow, can be categorized into two different things. So the flow could either be laminar or turbulent. I guess I should say, so I've gotten in the habit of doing a motivating example. So by the end of this video, we want to be able to answer this question. So I have a pipe that increases in thickness. So if you look at like the left to the right, it increases in thickness. And so there's like a gas over here, and then this is a liquid. And so we want to be able to answer the question, which fluid level is higher? Is it going to be higher on the left or higher on the right? We should be able to answer by how much as well, depending on, as long as we knew some parameters about the cross-sectional areas of the pipe. We have some pipe that is expanding in cross-sectional area. We want to know what that does to a fluid level underneath. So to answer that, we'll need both these topics. We'll need to understand a little bit about continuity and Bernoulli's equation. But first, I want to point out some of the assumptions that we're going to be using. So basically, the word laminar you can think of steady flow, and turbulent is like chaotic flow. And we are just going to focus. So everything we talk about for both of these is going to focus on laminar flow. So the picture that they used to use in textbooks used to have cigarettes, but they become more PC. So now this is incense. It looks like. So notice how the smoke, the fluid, it's pretty steady when it's first coming off this incense, and then it becomes chaotic. It becomes unpredictable in its motion. So if we saw a video of this, the laminar flow, we would see streamlines. If we looked at a particular point in space, the fluid around that point would be going at a constant speed. It would look the same over time. Whereas the turbulent, it would be, the fluid would be going one direction, and then a few seconds later, it'd be going in a totally unpredictable direction. So you could focus on a particular part of the fluid coming off of the incense, and that's a particular streamline. So we'll be focusing on streamlines when we talk about Bernoulli's equation and continuity. Okay. By the way, if you continue on in mechanical engineering, you'll learn about something called the Reynolds number, and this is a way of classifying fluids into whether we consider them laminar or turbulent. So it's a dimensionless number, and something like if the number is much less than like 2,000, the fluid is laminar. If it's much bigger, then it's turbulent. So it's kind of neat, but outside the scope of this class. Okay, so the first thing I want to talk about is continuity. So another thing we are going to, so this is one key assumption that we're going to make. Another one is that we're going to focus on an incompressible fluid. So sometimes this is a great assumption, like for water, basically any liquid. For gases, maybe it's a okay assumption, maybe it's not. So you really have to look at that on a case-by-case basis. So what is this saying? So if you have a pipe, and you have some fluid in this pipe that's going from left to right, basically the fluid is not going to bunch up at any one point. So you're not going to have, so overall, whatever fluid is going to be entering here is going to be leaving right here. So the fluid entering is equal to the fluid leaving. E-N-T-E-R. Fluid entering is equal to fluid leaving. So entering or leaving what? Well, just pretend there's a box right here or something. But really, we're focusing on what's going on right there and what's going on right there, right? So how are we going to quantify the amount of fluid entering and fluid leaving? Well, in terms of dimensions, we're going to look at the volume of fluid per unit time. So the volume of fluid per unit time that's entering is equal to the volume of fluid leaving per unit time. So we're going to have, we'll put square brackets just to give an indication that this is just looking at dimensions or units. So in terms of equations, what this is going to lead us to is the velocity times area, cross-sectional area. So this right here has some area, A1, and the fluid speed is equal to V1. So this is speed and cross-sectional area. So in other words, the fluid is moving from left to right. There's two dimensions that are perpendicular to that, and the streamline is going to define some area right there. So that whole area is A1. And then we can define similar things over here. We have V2 and A2. So this whole area right here is a funky looking arrow. It's A2. So V1, A1 is the volume per unit time of fluid entering, and V2, A2 is the volume leaving these, this box right here. Okay, so this is the equation for continuity. This is the main equation we want to focus on. And you'll notice if you look at the units here, velocity is meters per second and area is meters squared. So meters times meters squared is meters cubed on the numerator and then divided by seconds. So again, this is volume per unit time. This is called, so this right here is a volume flow rate. So if you have compressible fluids, you have to generalize this equation a little bit and multiply by density and talk about mass flow rates and just say, well, the mass entering is equal to the mass leaving. Because the densities don't have to be equal. But if we just focus on incompressible fluids, we can get away with just this equation right here. So the most common kinds of questions are that you'll see with this is you have a pipe and what happens if the radius, so it looks like, so we have some radius here, call it R naught, or actually most of these problems talk about the diameter. So let me talk about the diameter here. This is diameter D1, and let's say the diameter here looks like it's, how much bigger here? Say it's 1.5, 1, 2, 3, 4, 5, maybe 3. Let's just say it's 3 times D1. So if the diameter triples, and this is the most common mistake students make when solving problems like this, if the diameter triples, that means the area would increase by 5 times as much. So let me actually change the color here. Because now we're going to look at a particular numbers here. The A1 and A2 are completely general. If this is D1 and D2 is equal to 3 times D1, then that means that the area here is 9 times the area 1, since the area is proportional to diameter squared. Okay, so you might want to double check that you can reason that out right there. So if the area increases by a factor of 9, that means the speed of the fluid decreases by a factor of 9, if this equation is true. This V1A1 equals V2A2. So this is nice because we're going to want to look at different fluid speeds when we look at Bernoulli's equation, and this is a helpful tool to help us connect these two. So in a given streamline, we can connect the velocities if we know something about the cross-sectional areas. Okay. So this combined with the continuity equation would mean that V2 is equal to 1/9 V1. So already we have an idea here of where the fluid is not moving as fast. And I kind of already indicated that with the shorter arrows right here versus on the left. So on the left there are longer arrows because I know the fluid is going to be moving faster than it is over here, just because the cross-sectional areas are different. Okay. So that's the first half of this chapter. The second half is on Bernoulli's equation. So this first continuity equation, this could just be considered conservation of volume. So the fact that this is incompressible means volume is conserved, so the volume entering is equal to the volume leaving. Bernoulli's equation is a statement of conservation of energy. So I think it makes the most sense to write down what the equation is and then explain the pieces of it. Okay, so the proof focuses on a particular streamline and tracks energies, and you get a sense of how conservation of energy is involved. So I'm going to focus on a streamline. So this could be a pipe, or just, you have laminar flow and it's constrained, because it's somewhat steady, or it is steady, sorry. You know that the fluid that is contained within these dotted lines is going to stay within these dotted lines, right? Suppose you have some fluid right here, and eventually it goes up right here. And we want to make a statement about, so we want to use conservation to make a statement about what happens at this point versus what happens this point. By what happens, I mean, we want to talk about some properties that occur at point 2. So this is point 2 versus point 1. So some things that are involved here are the pressure, the velocity of the fluid right here, and actually the height in a gravitational field. So part of this equation is going to involve potential energy. And its potential energy, there's going to be a G because we're on the Earth's surface. And you have to keep in mind that, so you have to define the vertical direction upwards. So this is going to be height. This is going to be increasing height. So for example, if this is h equals 0 right here, then this is h greater than 0. You can't define downward to be negative the way we're going to write down Bernoulli's equation. So make sure you keep this in mind. So as a general rule of thumb, just define the lowest point in your problem to be h equals 0, and then all the other h's are positive. That'll get you out of trouble. Okay, so the actual equation is the pressure at point 1 plus 1/2 rho v1 squared plus rho gh1 is equal to, and then the same quantities, but all the subscripts I'm going to change to 2. So the pressure at point 2 plus 1/2 rho v2 squared plus rho gh2. Okay, this is Bernoulli's equation. Okay, so again, the P's are pressures. This term looks a lot like 1/2 mv squared, doesn't it? In fact, the units are very similar to 1/2 mv squared, except it's per unit volume, right? Remember, this rho is mass per unit volume. So it's like kinetic energy per unit volume. And all of these things have dimensions of energy per unit volume. It happens to be that pressure is energy per unit volume. So it's kind of like one form of potential energy. And then here's another form of potential energy. So it's like mgh, but per unit volume. So this is like gravitational potential energy, some other form of potential energy, stored because of the pressure of the fluid, and then the kinetic energy of the fluid. So this is how we can look at the pieces of Bernoulli's equation. But again, for more details, you could look at the textbook here to actually track the energy changes within the streamline. Yeah, so a lot of problems will simplify this equation one way or the other. In this particular example right here, this one, the original question. Suppose I'm gonna compare the pressure here and here. Okay, I don't want to worry about the height right here, and I'll explain why I don't have to really worry about that in just a second. But let's focus on a pipe that expands. It gets a bigger cross-sectional area. We want to focus on the pressures of those 2 points. We want to see which one is bigger. Okay, so for a particular example, we have a pipe that expands like this. We have some area A1 here. We have a bigger cross-sectional area right here, V2. So from continuity, we know V2 has to be less than V1, right? So remember, V1A1 is equal to V2A2. So if A grows, so if A2 is bigger than A1, then V2 has to be less than V1. Okay, so this is going to be some ingredient that we're going to use when we combine this with Bernoulli's equation. Okay, so let's look at point 1 right here and point 2. So we have pressure P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. All right, where did the where did the rho GH term go? Well, if these two are at the same height, right here, so rho GH is the same for both. So if H1 is equal to H2, I can just set one equal to the other, H1 equal to H2, and then cancel them out from both sides. So Bernoulli's equation will immediately simplify to this. So then it's pretty quick to see that if V2 is less than V1, okay, so I'm going to start with this. So that's going to be some quantity. And then now when I look at this term, that has gone down, right? That's decreased if V2 is less than V1. So that term on the right has gone down, which means the term on the left had to go up to compensate. This means P2 is greater than P1. The pressure at point 2 is greater than the pressure at point 1 right here. Okay. Now, back to this original problem. So the pressure here, so if we look at point 2 here and point 1, the pressure at point 2 is greater than the pressure at point 1. Now, because this is a gas, remember a gas has such a low density that the change in pressure is not very much when we go up or down the gas. You know, if we're just looking at a meter or so, it doesn't change very much. If you're looking at the Earth's atmosphere, then you would have to take into account, you know, these changes in height. And obviously near outer space, the pressure is 0, and then at atmospheric pressure, the pressure is 1 atm. But if you just look at changes of, you know, 1 meter or so, there's not much pressure change right here. So the pressure at point 2 is about equal to the pressure right here. Let's call this maybe 2 prime. And call this pressure, you know, call this point 1 prime. So pressure here at point 2 prime is equal to the pressure at point 2, and the pressure at point 1 prime is equal to the pressure at point 1. But this pressure has to be bigger than this pressure, right? From Bernoulli's equation combined with continuity. Remember, we needed the continuity equation to see that the fluid was not moving as fast right here. So the pressure here is bigger, which means it's going to be pushing harder on this liquid than this is pushing right here. So overall, there's a downward push right here, you know, relative to here. It's pushing pushing more down here. So that means that this fluid level is going to rise. So really, we need to revise this so that the fluid level up here is greater than right here. And by how much does it rise? Well, you can, so suppose this is settled to this point right here and this point right here, so we're in equilibrium. In equilibrium, this pressure needs to be the same. This is some well-defined pressure. So every point along this horizontal line is at the same pressure. So what you can do is you can say, well, the pressure here is equal to the pressure at this pressure, which is the same everywhere here, plus rho for this fluid, rho g times this distance is equal to the pressure here. And that has to be equal to pressure P2. Okay, so to write down the equation for that. So the original question. So the pressure at point 2, which is equal to the pressure at point 2 prime, is equal to the pressure at point 1 plus rho g, and then call it, it's going to be the delta h's between the two. So maybe just capital H, where capital H is this distance right here. So pressure here plus rho gh is equal to the pressure right here. And that's how you can solve for how big this is. So you could actually solve for P2 minus P1 if you knew something about the velocities, V1 and V2, and you knew something about the density of the fluid in the flow tube. You could actually solve for P2 minus P1 and then plug it in right here into this equation and solve for H.